My name is Gustavo Cortes, and I will be doing a mathematical modeling problem and solving it with differential equations. So our problem here is a man-made lake initially contains 200 gallons of water with 50 pounds of a chemical dissolved into it. A solution containing 3 pounds of chemical, 3 pounds per gallon of the chemical runs into the lake at a rate of 4 gallons per minute, and a well-mixed solution runs out of the lake at a rate of 4 gallons per minute. What is the maximum amount of chemical ever in the lake? So to start, we're going to set this up as a using a differential model. So I like using a little tank as an example, I guess. And then so here we got our flow in, and here we got our flow out with our solution already in it. So this is our 200 gallons of water with 50 pounds of chemical already in it. And so to set it up, we're gonna have our A's of t, which would be the amount of chemical after t minutes in the tank. So we have our dA over d of t, which would be our change in the amount with respect to time. So the change in the amount with respect to time is the same thing as what's coming in minus what's going out. So the change in the amount with respect to time is equal to the concentration of what's coming in times the rate that is coming in minus the concentration of it going out times the rate that is going out. So our concentration that's going in here is 3 pounds per gallon. So we have 3 times the rate that is coming in is 4 gallons per minute. And we're going to subtract that by A's of t over 200, which is the concentration that's going out because we're not given a concentration. So it's the same thing as amount with at a certain time over 200, which is the volume, and that's what concentration is. And then we multiply that by 4 gallons per minute because that's the rate that it's going out. So simplify this is 12e to the A's of t over 50. And then we set it up as a differential equation, and we have dA over dt plus A's of t over 50 is equal to 12. Now we're going to use a linear differential equation to solve this equation. This is our general formula right here, which is d of y over d of x plus p of x y is equal to q of x. So we're going to use the integrating factor method. So our integrating factor would be equal to e to the integral of 1 over 50, which is our p of x here. And that'll give us e to the t over 50. So we're going to multiply through by e to the t over 50. And that'll give us dA over dt times e to the t over 50 plus a sub t over 50 times e to the t over 50 is equal to 12 times e to the t over 50. Now this is the exact same thing on the left-hand side as the product rule of the derivative. So this is the same thing as the d over d of t of a times e to the t over 50 is equal to 12 times e to the t over 50. We take the integral of both sides, which will give us a times e to the t over 50 is equal to 12e to the t over 50 over 1 over 50 plus c. So now we divide our right-hand side by our e to the t over 50, which will leave our a sub t is equal to 600 plus c times e to the negative t over 50. So now that we have our solution here, we're going to try to find the maximum value. So to do that, we're going to need our c. So we're going to set our time when it's 0. And we know when it's 0, it's equal to 50 because up here we got containing 200 gallons of water with 50 pounds of chemical dissolved into it. So that would give us 50 is equal to 600 plus c times e to the negative 0 over 50. E to the negative 0 over 50 is just 1. So our c is going to be equal to negative 550. So we plug in negative 550 for c. And then we have our a sub t is equal to 600 minus 550 e to the negative t over 50. Now to define the maximum value, you would take the derivative and set it equals 0 and solve for t. So that's what we did here. We took the derivative, which cancel out the 600. And then we have negative 550 times e to the negative t over 50, derivative of this, times negative 1 over 50 is equal to 0. So we have 11e to the negative t over 50 is equal to 0. Divided by 11, e to the negative t over 50 would be equal to 0. So now we would solve for t, but because we have e to the negative t over 50, and it's already up here in our equation, e to the negative t over 50, we just plug in, to get the max, we would plug in 0 to t. But instead of simplifying further here, we just plug in 0 to the e to the negative t over 50, which would give us a sub t is equal to 600 minus 550 times 0. So our maximum value would be 600 of chemical at any given time.